Hey, welcome back. Today let's discuss nuclear stability. Now, to understand nuclear stability, we have to understand the relationship between mass and energy. Understand that in most chemical reactions, mass is converted into energies in most cases, but this is usually so small that we can't measure the change from mass to energy. Now, there is an equation that we use, a pretty famous equation, that we use to show the relationship between mass and energy. It's called Einstein's equation. So Einstein's equation looks like this: E equals mc squared. Now, what these letters mean is E is for energy, and this is in joules. M is in mass, which often is measured in kilograms. And C, if you remember from way back when we talked about particles and light, C is the speed of light, which is 3 × 10⁸ meters per second. Okay, so as an example, if I were to take a kilogram of coal, if I burned a kilogram of coal, only about 3 × 10⁻⁷ of it is actually converted into energy. The rest of it we can't see what happened to it. That's not really a lot of energy, right, from 1 kilogram of coal. But if we're dealing in something like nuclear chemistry, in nuclear reactions, the masses involved relate to energy in a much greater way. So there's a much larger transfer of energy from mass in a nuclear reaction. Say, for example, if I have lithium and I'm gonna, just bombard it with a proton, or if it gains a proton, right, then I have the formation of maybe something like this, where I form these two alpha particles. And this is just an example. This isn't anything that you need to see, but there is energy that's produced here. And if we were to calculate the total difference in the mass, right, so everything on this side, if we were to think about it, this has a mass of about, like 8.02329 grams. That's turning into 8.00520 grams. So you might be thinking to yourself, well, that's not that big of a difference in a change in mass. I mean, it's only a change in mass of anything that's to the 100th or 1000th place. But when we're talking about on the atomic scale, that's actually a pretty big deal. For example, this particular reaction that we see here is the equivalent of burning 136,000 pounds of coal. So before we talked about 1 kilogram of coal, this little equation right here is the equivalent of 136,000 pounds of coal, which is a lot of coal. So the short here is that nuclear reactions have the potential to produce a lot more energy than chemical or physical reactions. So let's kind of explore that by talking about nuclear stability. So understand that all atoms have a mass that is slightly less than the sum of all the individual masses in the nuclear particles. So if you take the individual masses of each of our known particles and you add them up, something's missing, right? And this is known as the nuclear binding energy. It is the amount of energy that's involved in the binding and releasing of these particles. It's also sometimes referred to as the mass defect. The greater the missing mass, the greater the nuclear binding energy, and that means the more stable the atom is. So the greater the missing mass, the more energy is involved in holding that atom together, which makes it more stable. So we can calculate nuclear binding energy, and luckily for us, we use the exact same equation for the relationship between mass and energy to calculate nuclear binding energy. So we use E, M, and C for this calculation. Now again, keep in mind that M reports in kilograms and E reports in joules. So it's going to be important to remember that, because as we practice this, we might want to move in and out of those different units. Let's take a second and let's get real specific with our masses for each one of our subatomic particles. But because before we used to say like, oh, it's about 1 AMU, right? But for calculations involving nuclear binding energy, we need to know the specific amount. So this is what it is. A proton isn't just 1, it's actually 1.0073 AMU. And a neutron isn't just 1, it's 1.0087 AMU. We've talked about in the past how a neutron's slightly more massive than a proton. Well, it is by, in the thousandth place. Electrons are small, and they are 0.005486 AMU. And yes, you need to go out to this level of precision, so keep that in mind. But this is an AMU, right? And we're going to be doing a lot of measurements in kilograms. We talked about that before. Now, if I wanted to write these in kilograms, it would be something like this. It'd be like 1.6726 times 10 to the negative 27th kilograms for a proton. I'll put a little arrow like this and I'll put kilograms. And then for a neutron, it's 1.675 times 10 to the negative 27th. And for an electron, it's 9.109 times 10 to the negative 31st kilograms. This is fine, but I think it's actually more important for us to know how to convert between AMU and kilograms. I think that will be a lot more useful to us. So instead, I would encourage you to just remember this, that 1 AMU is 1.66040 times 10 to the negative 27th kilograms. If you can remember this, then it doesn't really matter what we're given. We can always convert between AMUs and kilograms. So I think that's a more useful relationship for you rather than, just memorizing kilograms. So understand that this equation can help us solve for lots of things. We can use it to solve for kilograms. We can use it to solve for moles. We can use it to solve for joules. It usually reports in kilogram per atom. Sometimes it reports in kilogram per joules. Understand that it can do a lot of different things. Sometimes we even want to calculate things in something called joules per nucleon. And a nucleon is just like one subatomic particle. So A would be like something like a proton or a neutron or electron. So if we want to find out the amount of energy in just one subatomic particle, we would convert into nucleons. And we will practice that as we do practice with this. This is a blank that we don't need. We just keep going. All right, so let's give this one a look. So it says that we want to calculate the nuclear binding energy in joules per nucleon of each of the following isotopes. But I also want to calculate it in kilograms per atom. And I also want to calculate it in kilograms per mole. And I'm also going to do kilojoules per mole and joules per atom. And the reason why I'm kind of showing each of these steps is because those steps are going to help me get to joules per nucleon. Okay, so first thing we want to do is we want to separate iron into its 3 subatomic particles. So we have protons, we have neutrons, and we have electrons. And we're going to count up the number of each. So iron always has 26 protons. And this is iron, this is kind of close to 56. So I'm just going to assume that I'm basing my model off of iron 56. So then I'm going to probably have 30 neutrons. And then if this is a neutral isotope, then I have 26 electrons. Now I have to take each one of those and now multiply them by my new masses that I have. So I can't just multiply it by 1. I multiply it by 1.0073 AMU. I multiply this by 1.0087 AMU. And I multiply this by 486 AMU, excuse me. Okay, so I'm going to multiply all those things together, and then I'm going to add them up. Go ahead and give that a try, and then come on back when you're finished. Okay, so you should have gotten 56.450 AMU. Now I'm going to subtract that from 55.9349 AMU. That is the original mass that I was given. And this is going to give me the nuclear binding energy of 5301 AMU. And it's important to remember that this is AMU per atom. Okay, so now what I want to do, because I've now figured out AMU per atom, I want to start checking off the different things that I'm going to convert into. So let's first start by converting into kilograms per atom. So I'm going to take that number. I'm going to kind of make myself a little space here because I'm going to go a little wild. I have this 5301 AMU per atom. And I want to convert this number into kilograms per atom. So I want to take AMU, and I'm going to convert it out of AMU using that number that we learned before. So 1.66040 times 10 to the negative 27th. And I'm going to calculate that. So if I punch this into my calculator, I should find that I get 8.802 times 10 to the negative 28 kilograms per atom. All right, so now that I have kilograms per atom, let's take that number. So we're good with this. Let's take that number and now let's turn it from kilograms per atom into kilograms per mole. So now I'm going to go 8.802 times 10 to the negative 28th. And that's again kilograms per atom. And I'm going to use my relationship between atoms and moles, which is Avogadro's number. And I'm going to use that to get into kilograms per mole. And that is 5.299 times 10 to the negative 4th kilograms per mole. Okay, so notice that I'm kind of slowly walking my way towards joules per nucleon. We're getting there. It takes a little time. Now I am in 5.299 10 to the 4th kilograms per mole. I'm going to take that and I need to get myself into kilojoules per mole. So now that I'm in kilograms per mole, I'm now able to plug myself into the Einstein equation. And I'm solving for kilojoules now. So I'm going to just plug in. Mass is this 5.299. 5.299 times 10 to the negative 4th. The speed of light is 3.00 times 10 to the 8th. And I'm also going to put in a quick conversion to go from kilojoules into joules. And that gives me 4.77 times 10 to the 10th kilojoules per mole. Now that I'm in kilojoules per mole, I've satisfied one of those things. A kilojoules per mole is a really great thing for me to calculate. But I'm also interested in joules per atom. So I want to go back to when I was still in atoms, and I want to plug in my kilograms per atom, if you recall, that's up here. So I'm going to now do the same thing. Let's give myself a little more space. Kind of block this off. I'm going to now do the same thing. Let's get you out of the way too. Where I'm going to now plug in my mass, but this time I'm going to use the kilograms per atom, which is this number here, and I'm going to plug it into Einstein's equation. So that's 3.00 times 10 to the 8th. This time I don't have to actually convert anything. I don't need to get out of joules. So this is going to give me an answer in joules, which is what I want, 7.922 times 10 to the negative 11th. And that's joules per atom. This is the amount of energy per atom, which is great. I'm at joules per atom. And the reason why I got into joules per atom is because that provides me within striking distance of joules per nucleon, which was my original thing. Understand that I didn't have to go through all of these steps, but I'm just showing you all the different ways that we can calculate this. So we got one more. We're going to take that joules per atom, which is 7.922 times 10 to the negative 11th, and I need to convert this into joules per nucleon. So this is, again, joules per atom. And remember that a nucleon is just a subatomic particle. So how many subatomic particles do I have in total in this atom? I have 56. So I have 56 nucleons. And all I did was I added up the electrons, the protons, and the neutrons, and that's how I got the 56. Do that math, and I find that I get 1.415 times 10 to the negative 12 joules per nucleon. And you might be thinking to yourself, cool, why did we do all that? So understand that the reason why I did the first few conversions was to get myself into kilojoules per mole, because that's a really great unit that I can use to measure temperature and energy being released. And then I continued after that and found myself in joules per nucleon, because this is actually a really good metric that we can use to compare stability between different isotopes. And we will see that in a next example. So now that I've done this, kind of take it all in, make sure you run through it, maybe just to see why I did what I did. And I want you to see if you can try this one out on your own. So let's try out carbon. Before I just kind of throw you in there, understand that all I want you to find in this one is I just want you to find joules per nucleon. and I just want you to find kilojoules per mole. So however many steps you need to do that, that's all I want. I just want those two things. So I would start by counting up the number of subatomic particles, find the mass defect, which gives you AMU. You can convert AMU into kilojoules or kilograms per atom. As soon as you're in kilograms, you're allowed to plug into Einstein's equation. Plug into Einstein's equation, get yourself kilojoules, or get yourself joules, whatever it is that you're looking for, and then just kind of push your way through to the end. Go ahead and pause, give it a try, and come on back when you're finished. Okay, let's walk through. So first thing I do, I don't show this part of the work, but of course you'll have to do it yourself. I add up all the different masses for the different nucleons or subatomic particles to find the mass defect, which is an AMU, which I can convert into kilograms per atom. So that's that top thing at the top there. Once I have that number, I'm going to do two different things with it. And I tried to kind of color code it so you can see it. The first thing I do is I take that number and I convert it into kilograms per mole by using Avogadro's number. And then I take that kilograms per mole and I plug it into the E equals mc squared equation, and I solve for kilojoules per mole. Once I have kilojoules per mole, I'm done. Then I go back and I grab that kilograms per atom number again, and I just plug it into the E equals mc squared equation just by itself, as it always is. And that gives me joules per atom. Once I have those joules per atom, I just convert into joules per nucleon by just dividing by the number of nucleon. So it seems like a lot of work, but it's just kind of a couple steps. I feel like once you kind of get into the rhythm of it, it's mostly just unit conversions and plugging into an equation. It's not hard work, it's just wrist work, right? Let's try one more. This one, give yourself another pause. See if you can work through this one. We're dealing with uranium-238. Come on back when you're finished. Okay, same process, just different numbers. First, you find the mass defect by adding up all the different nucleons and subtracting them from the original mass. I convert that into kilograms per atom. I'm going to do two things with that number. First, I'm going to convert it into kilograms per mole, and then I plug kilograms per mole into the Einstein's equation to give me kilojoules per mole, and then I do the same thing with joules to get joules per nucleon. And then those are my two things. So again, both of these numbers are really valuable because one tells me how much energy is being released, and one can be used to compare stability. So which of these previous isotopes is most stable? Well, I can tell that by looking at the joules per nucleon. So I'm going to write that actually here. I'm going to say look at joules per nucleon. Remember that based on the definition, the higher the joules per nucleon, the more stable something is. So if I'm looking at the three, that one's 1.9 times 10 to the negative 12. This one's 1.24 10 to the negative 12. 1.45 10 to the negative 12. So I would say between the three, the iron is the most stable, which makes sense because iron is a pretty stable isotope, especially iron 56. That is a stable isotope of iron. And then you could ask yourself, okay, well, which one's releasing the most of atom energy? That would be what you look at the kilojoules per mole. I got 10 to the 10th on that one. I got 10 to the negative 10 to the 9th on this one, and 10 to the 11th in the uranium. So the uranium releases the most energy, but it is not as stable as the iron. So interesting thing to keep in mind. Another way that we can kind of tell this is maybe just by looking at them. Understand that low mass atoms, and by low mass atoms we mean atoms that have like 20 particles or less, with neutrons or proton ratio of about 1 to 1, are often going to be really stable, as opposed to those with larger masses are more stable when they have a neutron to proton ratio of 1.5 to 1. So sometimes we can just give it a look. If we notice that the ratios between protons and neutrons are way out of whack, then that's probably not going to be stable. But if they aren't, then they're probably going to be pretty stable. There's a good figure in your book that demonstrates this on page 722. It has kind of a graph with this nice line through it. That red line is called the area of stability, and those clouds are at different places where different types of emission are going to occur. So the A is going to be like where we have more neutrons than we do protons, so that means we're going to probably have something like we're going to be emitting a neutron, or we're going to have beta decay. The B up at the top is like alpha decay, and then the C over on the side, that's like positron decay. So there are different areas that describe different things. But again, it's mostly just calculations. You just kind of run through the different conversions to find out what you need. And that's it. That's nuclear stability. We'll see you next time.